Hi, I'm Thomas, and today I'm joined by my colleagues Sam, Arjuna, and Maggie to present the first two steps of Save the Egg Foundation's engineering design process towards the construction of a shockproof building. The first stage of the design process is problem definition. In the design of infrastructure, the consequence of vehicular impact and progressive collapse must be considered. The client approached Save the Egg Foundation to develop a shockproof building which could withstand such forces, and after further client questioning, the following problem statement was drafted. Humpty Dumpty is to be the sole highly fragile occupant of an apartment building located in Sydney CBD. This building will be subjected to the vehicular impact of a fast-travelling Tonka truck, a 5 kilogram dead load centred above Humpty Dumpty, and progressive decay to a minimum of 25% of the building's supporting columns. To protect Humpty Dumpty, the client, a property developer, has tasked Save the Egg Foundation with developing a prototype structure out of balsa wood, cardboard, paper, sticky tape, glue and string that is able to resist collapsing when such forces are applied. Due to its planned location, the client also requires that the structure is artistically appealing and is developed within a block of land with a maximum of 300 by 300 millimeter base and a minimum of 500 millimeter height. Furthermore, although the client requested that the structure not exceed 400 grams, they displayed a preference for a structure that was as light as possible. Optionally, this design, which is to be delivered on the 21st of April, will be used in the development of shockproof buildings globally to reduce the economic and social burden which results when buildings collapse from seismic activity. And here is a pause to read version of that. The quality of a problem statement is determined by its ability to define the problem in a manner which is free from unnecessary constraints and ambiguity, whilst also being concise. That is to say, a good problem statement contains just enough information to inform a plethora of ideas that all possess some capability to solve the client's problems. We strongly believe that our problem statement was able to achieve this. Firstly, it clearly outlined the client's tasks for our teams and only introduced constraints that for all future ideas must abide by, such as material and dimensional requirements and weight limits. The problem statement was also supported by questioning of the client to clarify various points of ambiguity, such as what type of car is being driven into the structure. The problem statement did not introduce any additional building constraints, thereby widening the amount of ideas generated in the concept generation stage. It also successfully outlined the 5 W's of framing a problem, which further aided in concept generation. But why is this important, you may ask? Well, problem definition is an integral part of the engineering design process because it not only guides future actions that fulfill the climate requirements, but it also facilitates the construction of a metric whereby all objectives can be graded based on their abilities to solve the problem. Further, identifying constraints to the problem definition is critical in preventing fundamental mistakes, such as a prototype that is too large. In the design of shockproof buildings, this is especially necessary to yield concepts that are viable in solving the client's problems. For example, a major constraint imposed by the problem definition is that the prototype must be able to withstand both collision and progressive decay and an applied dead load. By introducing this constraint in a clear problem definition, the team is unlikely to design a prototype which isn't actually shockproof, thereby avoiding a fundamental mistake. Clearly, by avoiding such mistakes and guiding the design process, a problem definition saves time and resources and reduces team member disagreements as all individuals better understand what is required of them and their teammates. Now on to Arjuna to explain the concept generation stage.
Yes, thank you, Tom. Hi, my name is Arjuna, and I'll be going through the second stage of the engineering design process, which is generating concepts and solutions. In the engineering design process, concept generation is fundamental in producing concept solutions which are able to, in some way, fulfill the client's requests. Clearly, this prevents the development of complex and incompatible solutions for the client, and so saves time, effort, and even money. Concept generation allows team members to experiment with various ideas before producing a solution, thereby widening the amount of concepts which can be generated and inclines a team to produce quality rather than marginally acceptable solutions. Additionally, because concept generation yields numerous solutions relatively quickly, it removes the team's temptation to consider their first idea a successful solution, hence making it more likely the team fulfills the client's requests. Evidently, the concept generation stage is necessary in the success of the engineering design process. A morphological, or morph, chart is a structured approach towards concept generation that is based around functional aspects that must be included in all concepts, as specified by the problem statement. The use of morph charts establishes numerous means to achieve a specific functionality. This chart helps team members identify the advantages and disadvantages of alternatives, and so effectively guides our execution of the project. A morph chart can produce a significant amount of concept solutions. For example, a 10 by 10 morph chart yields 10 billion possible solutions, all of which can be used to ascertain the best way to fulfill the client's requests in some capacity. It also provides insight into the best materials which a design could use. Now, brainstorming is a mechanism of concept generation where initial ideas to solve the client's problems are laid out roughly. It produces both concept solutions and means of generating other concept solutions, such as identifying the different types of braces that could be used in a building. It comprises both sketches and text to enhance the team's understanding of others' ideas as well as the task at hand. The images shown on this slide are screenshots of our brainstorming stage. Since our team only has 4 members, we revised the concept generation method of 635 brainwriting to whereby only 4 people review the creative ideas of other team members and generate 3 new ideas to fix any gaps in previous ideas within a 5-minute time period. It is useful as a concept generation technique as it increases team cohesion through individual contributions and ensures that each team member understands a specific concept. It also leads to many vastly different concept solutions. The mind map shown here is indicative of how the other 3 team members came up with unique design solutions to the original idea, pictured in the rough sketch on this slide. Now, I'll pass on to my fellow colleague Sam to explain some of our concept solutions.
Hi, I'm Sam, and today I'm here to tell you about our first 2 concept solutions which we have designed through the use of the concept generation tools as shown by Arjuna, including this morph chart. This is the morph chart we used for our first design. After consulting the group brainstorm and constructing a morphological chart as shown on the slide before, concept solution 1 was produced. Its primary feature is an octagonal holding bay made of cross-linked walls. Within this holding bay, a string and wool container hangs from the roof, holding Humpty Dumpty. This bay is then held up by vertical columns which are diagonally braced. This increases the resistance to collision while conserving weight, as diagonal bracing requires the least amount of beams. This structure is further supported by a series of inclined pillars extending outwards, which exist to prevent collapse when progressive decay occurs. To join beams together, dovetail joints will be employed, and these beams will then be connected to the foundation using mortise and tenon joints. Both of these joint types display exceptional resistance to tensile forces, and this solution is likely to be under 400 grams based on the research of the specified materials, although this cannot be confirmed until these materials are actually purchased. Consequently, this idea fulfills all the client's requests and so is a viable concept produced by our concept generation methods. This is the morph chart for our second concept solution. Solution 2 was generated using the concepts raised during the brainstorming and 635 brainwriting methods. By primarily incorporating sloping walls and inclined columns, the design is able to spread out the forces applied both vertically and horizontally. Cardboard would be used to create the sloping walls, which cushions the impact and provides higher tensile strength to the structure. Diagonal cross braces made of balsa add additional support to the structure and the main frame in order to withstand the lateral movement during the side collision as well. This type of cross brace is also featured on the roof in order to bear the 5 kg dead load. The main body of the design is based on a pyramidal structure to concentrate the forces away from Humpty Dumpty, whilst the inverted pyramid within the structure allows Humpty Dumpty to rest in a cavity through gravitational forces which fix his position. He will then be further protected by the surrounding cardboard walls lined with wool. This design also fulfills all the client's requests and so is a viable concept generated by our concept generation methods. Now on to Maggie, who will discuss our third solution and our next steps.
Hi, I'm Maggie. I'm gonna introduce the last concept solution to you, and this is the morph chart for design 3. After collaborative brainstorming, the use of the 435 brainwriting method within our group, concept solution 3 was created. As another alternative to solutions 1 and 2, it features a solid square base with vertical pillars splitting up, which allows for the use of diamond bracing in the walls. The joints of this bracing will be held together by strong wood glue and paper wrapping around the joints. This will account for issues created by progressive decay within the structure. The structure is also multi-level, featuring cardboard layers between each story in order to increase tensile strength within the internal structure. The use of layering also creates a floor structure which will be used to hold a string and cotton basket attached to the ceiling. And in order to support Humpty Dumpty, this will reduce the impact felt by him when the tower is struck, as it will cushion the forces. The Humpty Dumpty will also be protected by the heavy bracing and support beams around the cardboard roofing, which will hold 5 kg dead load. The final structure of this concept solution is the makeshift both wood and cotton guardrails, which will cushion the impact of the collision against the tower, reducing the overall forces and hence damage to the structure. Here's the conclusion for our project. So our next step is to analyze each concept solution and research different Shockproof structure, then select a reasonable solution to effectively fulfill the client needs.
On behalf of the Save the Egg Foundation, I'd like to thank you all very much for watching our presentation, and we hope that you'll consider our concepts in the design of any future shockproof buildings.